Welcome to Flink Forward Asia 2024.
Alright, ladies and gentlemen, we have in last presentation that we have three presenters. The name is Miss Satakshi Rush, Solution Engineer Confluent, Mr. Sivanshu Dubey, Advisory Solution Engineer Confluent, and Mr. Mustafa Banpurawala, Solution Engineer Confluent. They will talk about boosting GenAI precision with FlinkSQL, a streamlined GenAIOps strategy for lean infrastructure. So, give applause to Satakshi Raj, Sivanshu Dubey, and Mustafa Banpurawala.
Hello. Hey guys. I think it's the last session for today. You guys are tired, I think, and I will make it as interesting as possible for all of you. So, yeah, let's begin. The topic today that we are going to talk about is how do we boost the precision of our LLM GenAI models for lean infrastructure. And when I say lean infrastructure, basically it means that less GPU consumption or less infrastructure footprint for GenAIOps. In the previous session, we saw like how to build agentic system, like the inference side of it for GenAI, and in this part, we are going to see how to do fine-tuning, training, and subsequently increasing the precision of your GenAI systems. Okay. Yeah. So what's in there for the session for you today is first we will explore like what is the current scenario of GenAIOps in today's world. What are the challenges people are facing when using GenAI? The second one is like how we are going to tackle those challenges, and finally we'll see a demonstration, something in action to show you how this thing works. All right. So how many of you have already used ChatGPT? Like, can you give me a show of hands? Crazy. Yeah. So if you use GenAI or ChatGPT, and if you just generate a meme like this, which is around 1,000 token being generated from ChatGPT, it consumes around 40 to 80 GB of GPU memory, right? And like 42 GB GPU memory is around 10 cents of dollars being consumed in terms of money. While it creates 200 grams of CO2 into the environment, so which is very large. Like just 1,000 tokens. Just imagine, like just generating 1,000 tokens and you are creating 200 grams of CO2 into the environment. So how do you tackle this problem? How do you come up with a solution for this? Yeah. So even before discussing the solution, let's just talk about the problem in more detail. So here is a graph which shows the evolution of generative AI models along the way. So to begin with, like let's say GPT-4o is on the top, which has around like 600 to 700 billion parameters. So the more the data you have, more is the number of parameters you have on the model, more and the complexity of problem that it can solve is increased basically. So like larger the model, larger the data set it is trained upon, higher complexity problem it can solve. So GPT-4, that's why GPT basically outperforms almost every model on this planet. On the other hand, if you see the second yellow dot, which is Llama 2, Llama 2, Llama 3, these are like smaller models, 7 billion, 10 billion, up to 70 billion parameters models. So when I say 70 billion parameters, that means they are trained on less amount of data set, and that's why they can solve less complex problems compared to ChatGPT or GPT. So yeah, more parameter means more intelligence for solving complex problems. The second graph over here showcases how the GPU consumption increases with the billion parameters you increase on your model. So like let's say if you are having something like a 200 billion parameter model bigger than Llama, it will consume around 160 GPUs for training. This data showcases for training. This is not for inference. This is for training those models or creating those foundation models. And if you talk about GPT, which comes around 600 billion parameters, it requires like 640 GPUs together into a cluster to fine tune that model and create them out of it. So, and more data being available in the world showcases our evolution towards artificial general intelligence. So, when I say artificial general intelligence, it means it can answer almost any question of the world. Recently there was a stat which says the complete data of the entire world comes into 10 trillion parameters. So already we are almost at 1 trillion right now, and as we grow along the way with more and more data, this thing will grow, and more GPU consumption will come into play when you train these kind of models. Alright, so to conclude what we just saw, there are like models which are bigger models like OpenAI, Anthropic, Gemini models, which are almost 400 to 800 billion parameters. They can solve more complex problems. They have good reasoning, but their size is also large and hence the GPU consumption. On the other hand, we have smaller models like Llama 3, Llama 2, Mixtral, which are smaller in size, more cost efficient, less GPU consumption, but they can't solve like many very complex problems, like the way the left side ones can do. So, along the way of our conversation, we will call the left side models as mega models and the right side ones as tiny models. And yeah. So, coming to the problem statement, this is like the background of how things are evolving, how data is evolving, how models are evolving, how solving complex problems is evolving. And now what we want to do actually is, we want to consume less GPU, we want to have less infrastructure footprint, but at the same time, we want the model to be solving more complex problems. So how we do that? So the way to do that is, increasing the accuracy, the knowledge of your smaller models using the bigger models. Bigger models are, you can think of like a professor teaching to a student. The student doesn't know a lot of things, but a professor has a lot of research being done in past years. So professor can impart some knowledge, some ideas into student, and then student go and execute it. And how we do that is using knowledge transfer with fine-tuning and evaluation pipelines. But the main catch over here is people are already doing fine-tuning. People are already evaluating new and new models. But what different does it make if we do it with streaming? Why do we need streaming in this? Why do we do it with Flink, to be more specific? So let's deep dive into that solution particularly. My colleague Mustafa will take over this and try to explain more in detail.
Hi guys. So as my colleague talked about, the intent is always to use a small model with more knowledge and save money instead of using the high model. But then again, the large model have more knowledge, so it will give you more robust answers to your relevant queries or relevant input. So for our pipeline, what we are doing is we're taking input data set. Now this input data set could be anything. This could be stock taker information. It could be a clickstream data. It could be a geolocation. Basically, if you're opening a Google Maps, whatever where you are, where you want to reach, those kind of inferences, that could be input data set. So for our pipeline, what we are doing is we're taking the stock example wherein we are capturing stock related information at regular interval of time. It could be 1 minute, it could be coming at 1 hour, it could be coming at 1 hour. So next. So what we do is we take this input data set and create a fine-tuning data set. Now this fine-tuning data set is nothing but conforming it to the Flink side of things, wherein we apply the necessary watermarking and bucket it into some regular interval for some consistent analytics. So let's say you have stock related information which is coming at random intervals, but your aggregations on analytics, your responses from your LLM models needs to be on some sort of a windowed, some sort of a 1 hour window, some 1 day window or 1 month window. So this is what we are doing with Flink. We are passing into some fine-tuning processing wherein we apply the necessary watermarking to these proper bucketing and then push it into the large models. Now this large model generates for us the ground truth. which is basically the real answer for your responses. So if you want to do a 5-day aggregation on your particular stuff, so the large model will generate for us the ground truth generation, and this output will be used by the Flink pattern or the GenAIOps pattern that we are suggesting to fine-tune this low-level model. Now the output of this ground truth of the large model will be used as a training data set. Now the output is in the format of context, instruction, and response. Now context is basically the window, which is basically saying, hey, I want to, based on this raw data, just generate me a 3-hour, average of this stock price, or it could be anything. So that is your context. Instruction is basically computing that, do the aggregation for me. Just giving that instruction to the model, saying, hey, do this for me. And the response is basically the real value. So whatever we push, the raw data that is pushed to the large model is generated as a training data set in this structure of a context, response, and instruction. Now once this training data set is created, we push this data into some blob storage and trigger a fine-tuning pipeline. Within this fine-tuning pipeline, what we do is we take this version 1 model and push it into version N, which is basically the iterative way of enhancing this low-level model into more refined, more knowledgeable model, at the same time reducing the GPU required for it. Now within this fine-tuning process, we are incorporating some evaluation criteria. Basically, we are giving in checks to understand whether we are moving in the right direction or not. When you are fine-tuning this low-level model to some version N, we do not want to move into a certain direction where the model starts hallucinating or getting some wrong responses. So for that, we have incorporated evaluation pipeline, which is basically whatever data that we have created in fine-tuning data set, we sample out some test data out of the fine-tuning data set, and then run the same response. We do some sort of inferencing on both these models. So if you have a version N model and we have the large model, we run the same response, same input on both these models and compare the responses. Now these responses are evaluated, and based on some parameters, some threshold values, we identify whether your model is moving in the right direction, whether it is getting enhanced, knowledge base is getting enhanced, and accordingly we identify some sort of cutoff.
Yeah, and there is a catch in this architecture as well that so when we do evaluation, we are doing evaluation with a generative AI model itself. So what you can essentially do is you can just write a prompt, you can have your expected response, which is your ground truth, and then you can have your actual response from your smaller model, and then you can have evaluation based out of like some more different model like OpenAI and say, okay, like now I want to have a comparison between these two responses and want to generate some kind of evaluation metrics out of it. So
yeah, so once we have done this evaluation, once we identify, hey, for some records, this model is not giving the required answer or the required necessary answer, we identify those records and then push it back into the same fine-tuning pipeline. Wherein this data set will be again used to fine-tune and create a new version of your low-level model. So it is an incremental or iterative way of getting to that model wherein your low-level model starts behaving or starts mimicking your large models with a small amount of parameters.
Right. So exactly like this, the same analogy, right? Like a professor and a student comes into a college, he doesn't know anything. That is your base model, your foundation model. And then there is a professor, which is Gemini or GPT, right? So that professor is imparting the knowledge day by day in smaller windows, in smaller chunks. And at some point of time, that student will start to behave or, like give knowledge to somebody else in the same way that professor used to give. So this is that all analogy is all about. And so I'll hand over to Sakshi, my colleague, for the demonstration of this pipeline. Thank you.
Yeah, hey, hi everyone. Thanks to Mustafa for explaining the architecture, explaining the concept of why should we do what we are proposing. But things always look better in action. So let's see a demonstration of how do we implement what we are proposing, right? Just to set the stage a little bit and to give you some context, we're actually using managed Flink service on Confluent Cloud, which has its own SQL editor and also has created some pre-built functions to register and invoke your models right alongside Flink. So if you still want to do it with open source Flink, it's still possible. You might have to write your own functions, or there's also this flip that's created which you can track. It's called Flip 437. if it has piqued your interest, it's definitely something to keep an eye out on. With that,
also like just to add on top of it, so Flink 437 is exactly what we are going to demonstrate in this demo, because Flink 437 says that introducing a new function into the set of predefined functions in Flink, which supports integration with different GenAI model providers. So yeah.
Yes, so the first thing we want to do is, of course, generate our input data set. We talked about our demonstration is going to be on stock ticket data. So first we're doing that, and then we're sending it all to Flink. You can send it by Kafka, you can send it directly to Flink, however you want to do it. So for our demo today, it's because we're built on Content Cloud, it's going to a Kafka topic, and then from Kafka topic, Flink is the Flink table is getting all of the data. So if you want to see the data in here, you can have a look at that. Yeah, so these are the values that your input data set is going to contain, and this is what is going to, this is where we'll start. So next what we are going to do is, we are going to deploy, like, of course, a tiny model, which is pre-trained, it's not going to have, not going to give better outputs, and then there's going to be a version 3, like an incremental better version of the same model, which also we're going to deploy right now. But how is that happening? We'll have a look at. We're going to use create model statement to do that. Create model in Flink on Content Cloud, you can actually register your own model in your Flink environment. We're also going to deploy a better model, which is our mega model, Gemini Flash 1.5, to generate a ground truth. So this model is going to receive the instruction and the context, and then create the response that we just talked about. And if you want, so this is our fine-tuning pipeline. This is where all the instruction, context, response is going to be saved. And this, just have a look at what the schema is going to look like. Yeah, so we're going to send all the parameters, and the response is going to be generated by Gemini. Of course, first we have to create our, the sticker data is not good for pre-processing, it's not watermarked, so we first introduce a timestamp, add watermark, do pre-processing. That's essential for Flink to work on the top of this data. And then we wanted to create a window of the data that we want to use, right? Because we want to perform analysis over like a 3-hour period of the data that's coming in. And so you can also do that very easily with FlinkSQL using Windows, and we're going to use Tumble in here. And then we can, use Gemini to create a ground truth, and then we're going to send all of this. Yeah, so in here, if you see, this is the mn predict function, which is what is the function that is going to call your model, invoke your model. We're going to send the context, the prompt, and then this model is actually using this prompt and generating the response for you. So it's going to do the technical analysis right now based on the data that you sent to it. So if you want to see the response that got generated, so this is the response that got generated. So we sent ahead an instruction, a context, and this is how the response looks like. It has some technical analysis values that if you work with stocks, you would understand a little bit better than me. So what we're going to do next is, of course, we need to do the actual fine-tuning, right? So we're going to send all of this data to an S3 bucket. You can send it to any object storage, and then we're going to move a little bit out of FlinkSQL, and what we want to do now is we are going to sending it all to S3. You can again send it via Kafka, you can send it directly from Flink, and once that is done, so all the data is now in S3, and then we want, this data is actually not formatted for further down processing, so we are going to format it a little bit, make it better, just remove all the anomalies that would hinder the performance of your model further down the line. Yeah, and then we're going to define a prompt template for fine-tuning. So this is when your actual fine-tuning would happen. And before we do that, what we're going to do is we are going to, we also tested let's test our template also. And then we're going to this fine-tuning data set that just got created. We're going to split it, right? We're going to split our training and test data. The test data is going to be sent to Flink via Kafka again to the evaluation. And we're going to use a subset of it to also train our model, make it incrementally better. So this is what is happening in here. So we split the data. The test data is now in Flink. If you see, it's visible in our SQL editor. But let's complete our training pipeline first here. So we are going to send our training data set and the fine-tuning prompt template that we just created to SageMaker. And then we are going to, so it's sent, and then we are going, so basically this is making our model better. And then we're going to deploy the post-trained model, which in our case is going to be the third iteration. Over time we fine-tuned our tiny model a little bit, and then we're going to deploy this model, and then we're going to compare the response, what our pre-trained model would have generated, what our post-trained model is generating, and going to compare both these responses against what Gemini would have given as a response. So if you see, this is the response that's generated by both pre-trained, post-trained models, and the earlier one should have been ground truth. Yeah. So over time, post-trained response is getting better and better. And now again, we are going to use Gemini, again, a large model, to also do the evaluation. Like, tell me this is the pre-trained, post-trained, and you have your own response. Tell me how is the model behaving. Is it accurate, is it not? Give me some metrics, so this is what the metrics would look like. And how do you do it for real-time streaming data? This is what we're going to show now. So of course, we first have to create like a table in Flink where we're just going to store your pre-trained, post-trained, and ground truth, all these responses that we can compare against each other. Yeah. So if you see here, this is what we do. Now, but what we're going to do is we're going to call our small model to generate the pre-trained response, our version 3 model to generate the post-trained response, and we already have the responses from Gemini, which we got, right, the ground truth that we generated earlier. So let's have a look at what the response is. Yeah. So if you see, some response got generated, and then we're going to have some evaluation metrics that again would be generated with Gemini. Let's have a look at how we do that. Yeah, so these are the metrics that Gemini would create for me, compare my pre-trained and post-trained responses to the response that it would have given, and give it a score based on a few different factors. So let's now create evaluation metrics. So we're again going to invoke Gemini, give him an instruction to do, like, hey, this is, I want to compare these two models, generate a score for me, and this is what will happen. So once those metrics are actually generated, of course, not all the data is going to be accurate in the third iteration itself. It's going to get incrementally a little bit better. Some data that you feel is not right, you're going to, with lower score, you're going to figure those data out, which have a lower score. In our case, it's going to be less than 0.7, 70%, less than 70% faithfulness score, not good enough for me. Send it back to the fine-tuning data set. This is the feedback loop that you would send it back to, and then on the basis of this, if you see the example that's given here, so out of those values, it's not generating a good score. So I sent it back ahead to the fine-tuning data set, and so the loop would again go on until the score is what we want to achieve. So this is how it would work. Yeah, so it got added because it wasn't good, and hoping it will get better with time. Yeah, so this is how you can use Flink to evaluate and fine-tune your models, your smaller model with time. And I'll again call upon Shiv to discuss further.
Oh, thank you, Satakshi, for the wonderful demo. So why do you want to do this with streaming dataset? That is the first question, right? Because we want the model to become accurate with time immediately. Let's say, talking about a bank fraudulent transaction detection, okay? Patterns can change along time. Like, let's say if somebody is doing some fraud in an XYZ manner today, he can do fraud in an ABC pattern tomorrow. So how will your model will come to know immediately that, okay, now ABC is the new pattern that I have to detect? So with streaming dataset, with windowing operations, you can keep on creating those new training dataset again and again and again. And basically you're versioning your models basis of your checkpointing of the Flink dataset itself, which is going to give you the accurate result as early as possible, right? Talking about like what are the challenges of this architecture? As of now, we have discussed a lot of things, but there are a few things that we have to keep in mind before implementing something like this. One of the biggest challenges is over-tuning. How do you make sure that if you are doing training again and again with like some window of dataset, how do you make sure that your model doesn't become biased? Where are you going to cut off your fine-tuning pipeline? How will you come to know that? So that is one of the biggest challenges that still have to be solved with this kind of architecture. Second is, how will you enforce the best evaluated model always? Your evaluation metrics can change. You might need, for example, like today you want faithfulness is 0.7, tomorrow you want biasness is 0.3. So how do you make sure that your best evaluated model gets enforced always for your inferencing purposes? And the third challenge is contextual awareness. So if you have seen in this example, we are generating technical analysis on basis of, let's say, 5-day moving average. But 5-day moving average cannot be created out of 30 minutes of time window. That's technically not possible. So how will you bring the, the earlier data into the context of processing? And for that, like, maybe I can give you a hint. You can think of stateful processing or managing state in Flink and do something like contextual retrieval with that for inferencing in the next step. So these are some of the challenges with this architecture, but yeah, these are not like something impossible to solve. We can always solve it with Flink's time and state management capabilities. And yeah, that's pretty much for today. Thank you.